Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel. Today we'll take a quick look at a real-world capacitor charge and discharge circuit. We'll see if cold hard reality matches our theoretical expectations. This demonstration operates under the presumption the viewer is intimately familiar with both the capacitor charge and capacitor discharge process. Additionally, it's presumed the viewer has a degree of mathematical competency, can determine electrical properties at specific times, and solve for times that satisfy specific conditions. Our circuit of interest consists of an 18-volt DC source, a super large 6,500 microfarad capacitor, and a knife switch that toggles between two resistors. In position 1, the switch serves to charge the capacitor through R1, a 1 kilo ohm resistor, and in position 2, the switch serves to discharge the capacitor through R2, also a 1 kilo ohm resistor. The capacitor is initially uncharged and exhibits no voltage differential across it. Instrumentation is configured in the following fashion. Voltmeter 1 measures voltage across R1, positive to negative, left to right. Ammeter 1 measures current through R1, in to out, left to right. Voltmeter C measures voltage across the capacitor, positive to negative, top to bottom. Ammeter C measures current through the capacitor, in to out, top to bottom. Voltmeter 2 measures voltage across R2, positive to negative, left to right. And finally, ammeter 2 measures current through R2, in to out, left to right. Here's the real-world setup we'll be using today. All 6 DMMs will allow us the luxury of watching this charge and discharge process unfold in real time. Let's examine the capacitor charge process first. Step 0, do the calculations first. Let's see if our observations match our expectations. First, see if you can calculate the time constant for the capacitor charging process. Then, determine the initial conditions for elements in this system. Finally, determine the final steady-state conditions for elements in the system after a full charge of 5 time constants. By all means, pause the lecture and try this on your own. If you're tracking, you should have arrived at the following values. The time constant for the charge circuit is the resistance value of R1 times the capacitance value. Substituting in the given values of 1 kilo ohm and 6,500 microfarads, we obtain a time constant of 6.5 seconds. This is a super large time constant for 2 important reasons. 1, R1 presents a fairly large resistance value at 1 kilo ohm. And 2, most importantly, the capacitor is astro-freaking-nomically huge. 6,500 microfarads. That's like a super tanker for charge storage compared to the little peapod capacitors you might be used to using in lab. A complete charge will occur after a time span of 5 time constants, or 5 times 6.5 seconds, or 32.5 seconds. Conveniently, this large time constant will allow us to see the charge process unfold in real time without the use of special purpose instrumentation. Additionally, by recording the charge process, we'll be capable of pausing the demonstration whenever we desire to take a look at instantaneous values at specific times. At the onset of the charge process, the initially uncharged capacitor can be modeled as a short circuit. Voltage across R1 will be 18 volts, and voltage across the initially uncharged capacitor will be 0 volts. Ohm's law demonstrates R1, and every element in series with it will experience an initial burst of 18 volts over 1,000 ohms, or 18 milliamperes of current. Given the switch in position 1 isolates R2, no current will flow through it and no voltage will be dropped across it. These are the start points for the charge process. After 5 time constants, or 32.5 seconds, the fully charged capacitor can be modeled as an open circuit. At t equals 32.5 seconds, current through both R1 and the capacitor will have ceased, and 18 volts will be dropped across the fully charged capacitor. At the end of the charge process, both I1 and IC will be equal to 0 amps, V1 will be 0 volts, and VC will be 18 volts. These are the endpoints for the charge process. We have the start points, the endpoints, and the time constant. See if you can derive the time-variant expressions for current through R1 as a function of time, I1 of t, voltage across R1 as a function of time, V1 of t, current through the capacitor as a function of time, IC of t, and voltage across the capacitor as a function of time, VC of t. I wouldn't worry about deriving expressions for R2, since it's effectively isolated during the charge process. By all means, pause the lecture and try this on your own. If you're tracking, you should have arrived at the following values. I1 of t equals 18 milliamperes times e to the negative t over 6.5 seconds. Current through R1 will experience an initial surge of 18 milliamperes and drop to 0 over 32.5 seconds. V1 of t equals 18 volts times e to the negative t over 6.5 seconds. Voltage across R1 will surge to 18 volts and drop to 0 by 32.5 seconds. Given this is a series circuit, IC of t also equals 18 milliamperes times e to the negative t over 6.5 seconds. Current through the capacitor will experience an initial surge of 18 milliamperes and drop to 0 over 32.5 seconds. Finally, Vc of t equals 18 volts times 1 minus e to the negative t over 6.5 seconds. Voltage across the capacitor will start at 0 volts and rise to 18 volts by 32.5 seconds. Now that we've got the time-varying expressions, let's try some instantaneous analysis. See if you can determine the instantaneous values of current and voltage for all elements involved in the charge process at time t equals 5 seconds, just a little bit before one time constant. Additionally, see if you can determine the time value when the capacitor is charged up to 12 volts. Once you've solved for this moment in time, determine the instantaneous values for the remaining properties at this same time. By all means, pause the lecture and try this on your own. If you're tracking, you should have arrived at the following values. Substituting 5 seconds into our time-varying expression for voltage across the capacitor demonstrates the capacitor will have charged up to roughly 9.7 volts 5 seconds into the charge process. An application of Kirchhoff's voltage law demonstrates that R1 experiences a remaining 18 minus 9.7, or roughly 8.3 volt drop. An application of Ohm's law demonstrates R1 will experience 8.3 milliamperes of current, as will the capacitor. For our second set, algebraic manipulation demonstrates the capacitor will have charged up to 12 volts by roughly 7.1 seconds. At this same moment in time, an application of Kirchhoff's voltage law demonstrates R1 experiences the remaining 18 minus 12, or 6 volt drop. An application of Ohm's law demonstrates R1 will experience 6 milliamperes of current, as will the capacitor. There you have it. Not only have we modeled a complete charge process, we know the instantaneous values of electrical properties at specific times. Let's see if cold hard reality meets these expectations to a reasonable degree of accuracy. I'll let the charge process run through once with some minimal commentary, and then go through it again, stopping at specific points along the way. The moment the knife switch is moved to position 1 at t equals 0, we start the charge process. Current through R1 and into the capacitor experiences an initial spike, which then starts to subside. Voltage across the charging capacitor rises. As current tapers off, voltage across R1 also drops. After 32-ish seconds, voltage across the capacitor stops at roughly 18 volts. Current through the charge circuit also stops. This ends the complete charge process. Looks good so far. Let's see if it passes close inspection. Let's start the charging process again and pause it along the way for some thrilling play-by-play commentary. This time we'll zoom in on the meters for the elements in the charge circuit, notably R1 and the capacitor. The moment the knife switch is moved to position 1 at t equals 0, we start the charge process. The initially uncharged capacitor starts the charge process at 0 volts. Current through R1 and into the initially uncharged capacitor spikes to roughly 18 milliamperes. Five or so seconds into the charge process, it looks like voltage across the charging capacitor has risen to roughly 9.6-ish volts. This is super close to our anticipated value of 9.7 volts. When voltage across the charging capacitor has risen to roughly 12 volts, 2.1 or so seconds later, t equals roughly 7.1 seconds, current through R1 and into the initially charging capacitor has continued to drop to roughly 6.3 milliamperes. This is super close to our anticipated value of 6 milliamperes. Voltage across R1 has dropped to roughly 6.2 volts. This is again super close to our anticipated value of 6 volts. The rest of the charge process slowly unfolds until the capacitor eventually reaches a final voltage of roughly 18 volts. Current through the charge process ceases altogether at roughly 32.5 seconds. This is exactly what we anticipated.